you are in the world. Welcome to this electrochemistry webinar for a new product, ElectroReact. But without further ado, I'd like to thank you all again for attending. We really appreciate your time. It's an exciting new area for Asynt, electrochemistry. We've since this products for so many years, but yet this is our first electrochemistry tool. And we're really grateful to Professor Nick Kapoor and Dr. Charlotte Willans bringing us this novel idea that they developed together to solve many of the problems that they could see, to make it easier to get on and do electrochemistry in the laboratory without great expense or without reliability issues. Go on to the talk itself. Just to say that we'll be taking questions via the chat, in the chat section of Teams. So any questions you have as we go through the webinar, please pop them in there. My colleagues at this end will then look at those as we go. And at the end of the presentation, we will then try and answer all those questions for you at the end. Just bear with us. Anyway, so again, thank you very much to Nick and Charlotte. I'll pass it over to them, and they'll introduce themselves in a bit more detail, and we'll get on with the presentation.
Thanks, Martin. Just check those slides have come up for you. Great. So thanks for the introduction, Martin. So myself and Charlotte are going to talk to you today a little bit about how ElectroReact came about, how we're using it in the laboratories, and how we've chosen to support it through the website. So hopefully lots of information about how to use a product such as this. So by way of introduction, my name is Professor Nick Kapoor. I'm a chemical engineer. I work at the University of Leeds, and I guess much of my research is around creating very controlled fluidic applications. And these include with chemists. So we've developed the FreeActors, which is a flow chemistry platform with Asynt in the past, and then added on the photochemistry element to that, so the photo FreeActor. And I've worked with Charlotte for probably about a decade now. And part of the work we've done is about creating a really robust electrochemistry platform, the ElectroReact, that we'll talk to you about today. Charlotte will introduce herself in a moment, but part of this work has been carried out at the University of Leeds. Charlotte's now at the University of York, but we've both been involved and continue to be involved in the Institute of Process Research and Development at Leeds, which forms a bridge between chemists and engineers, and is very much about taking solutions, practical solutions into the world of chemistry across many fields. And we have really good industrial supporters and an industry club that we run as part of that. So I'll hand over to you now, Charlotte.
Thanks, Nick. So I'm Dr. Charlotte Willans. I'm currently at the University of York. My research area is organometallic chemistry and organic chemistry. And then within the context of the ElectroReact, we're interested in developing electrochemical synthetic methods to organometallic and inorganic compounds. And when we started working in this area around about 12, 13 years ago, we were coming up against many challenges in terms of reactor design to enable us to do the type of chemistry that we wanted to do. So that's when we started chatting with Nick, talking about these challenges and the requirements of a reactor that would solve these. So looking at some of those requirements, a lot of our chemistry is air sensitive. We need to do chemistry under inert conditions. So as an example, in that top left hand box, you can see the formation of ion complexes. On the right hand side, the reaction is done under aerobic conditions and we access iron 3 complexes. But if we can eliminate air from that reactor, electrochemically we can form iron 2 complexes. It's also ideal to be able to do parallel screening of reactions. So as an example, on the right-hand side, we have an oxidative coupling reaction to form these sulfonamides, which we took from the literature. And originally, we weren't able to reproduce this. And this was because we were moving from a different reactor system to what was published in the literature. So we very quickly optimized this reaction in our ElectroReact, or at the time, it was our bottle reactor. And you can see by varying the potential or the current, we can run at constant potential or constant current, we were able to go from no product at all up to 58% yield. Within a lot of chemical reactions, including electrochemical reactions, we want to be able to monitor reactions. So we need to be able to withdraw aliquots out so that we can analyse them over time. So the example on the bottom left-hand side, you can see the conversion as a function of electron equivalence, which is the same as time. And by looking at that, we can see that for this reaction to reach almost full conversion, we need around about 1.6, 1.7 electron equivalents in that reaction. And then, of course, if we're doing electrochemistry, we're doing electrosynthesis, we want to be able to do some analytical electrochemistry, so running some cyclic voltammetry. And in order to do that, we need to switch out the power pack that we use to do our electrosynthetic reactions and replace that with a potentiostat. So working with Nick, we developed our first reactor, which we called the bottle reactor. And this was published in OPRD a few years ago. So you can see the reactor there on the left-hand side. Within that reactor, we have, at that time, it was a PTFE insert. And you can see the slots that allow the electrodes to be slid into that insert. And they're secured with a grub screw on the side. And it doesn't matter what electrodes are used in there, they're always at a fixed distance apart. And then key to this reactor are two additional ports on the top of that insert, and different attachments can be added to those ports. So they can be blanked off with a blanking screw. The one on the far side has attachments, so this can be connected to a Schlenk line, so reactions can be done under inert atmosphere. We can insert needles through there so that we can withdraw samples over time, or we can add reagents over time if that's what we want to be able to do. And also we can switch out the power pack for a potentiostat, so we can do cyclic voltammetry. And you can see on the right hand side, we also machined a plate that sits on a stirrer hot plate so that we can do 6 reactions in parallel on there. So I'll just give a few examples of the types of reactions that we did after we developed that bottle reactor. So on the left-hand side, you can see the electrochemical formation of copper NHC complexes. C1 is a neutral complex. C2 is a cationic complex. But if we can withdraw aliquots over time and monitor this reaction, you can see that the formation of C1, which is the blue trace, is more efficient than the formation of C2. So for C1, we need 1 electron equivalence to get full conversion, whereas for C2, we need nearer 2 electron equivalents. Similarly, on the right-hand side, the formation of the copper triflate, we can monitor that reaction over time. Theoretically, only 1 electron equivalence is required for this reaction, but you can see that we're nowhere near full conversion, whereas once we get to 1.5 electron equivalents, we have full conversion of that. So it enables us to optimize these reactions by withdrawing samples over time and monitoring those reactions. So as I mentioned, a lot of chemistry, whether it's chemical reactions or electrochemical reactions, require inert conditions. So these are just some examples that we've carried out in the bottle reactor. So on the left-hand side, you can see some gold NHC complexes, some iron 2 NHC complexes. These are very air-sensitive materials, particularly the iron 2, and we can form them cleanly in high yield in that reactor. On the right-hand side, this is similar to the iron chemistry, so making these Salem complexes. If we do the reactions under hydrous conditions, if we have air present in there, we get to the manganese 4 complexes. But on the left-hand side, we've been able to do this under inert conditions and form those manganese 2 complexes cleanly and in high yield. And then moving on from there, we've also been able to do cyclic voltammetry using that reactor. So through one of those additional ports at the top, we're able to insert a reference electrode, which enables us to do our cyclic voltammetry. And as I mentioned before, connect a potentiostat. On the left-hand side, it's the cyclic voltammograms of a range of imidazolium salts, so to form the carbene complexes. And on the right-hand side are the CVs of some metal salts. So since we developed the bottle reactor, we've worked with Asynt to develop the ElectroReact, which Nick's going to talk about in more detail. But just to say that we now use this routinely in our lab. It's a really flexible piece of equipment which enables us to use it across a broad range of different research projects. We have undergraduate MChem students using it through to PhD students and postdocs, and they pick it up very, very quickly. So, you know, as soon as they're in the lab, they're picking up the technique and they're able to do electrochemical reactions very quickly. So I'll hand over to Nick to talk a little bit more about the ElectroReact.
Thanks, Charlotte. So what we did after we started working in this area was sat down and looked at all of the controlling factors around an electrosynthesis. And of course, some of these are around the chemistry, so things like the purity of your reagent, your solvent, the electrolyte that you might add in there. But quite a few of these are actually as a result of the reactor itself. So if we look at a picture of the reactor over on the right-hand side, there's just a cartoon sketch here. Things like the purity and the type of metals of your electrodes are really important. The geometry, so the spacing between those electrodes is really important, whether you're working in a divided or an undivided cell. And of course, this is an undivided cell, so there's no semi-permeable membrane between the two electrodes. And then also things like the conditions that the fluid's in, so the degree of mixing, the temperature, and also the atmosphere. So Charlotte's already alluded to some reactions that are very sensitive to oxygen, for instance, and actually being able to control these is really important. So although the technology looks really straightforward, and in many ways it is very easy to use, by using the ElectroReact platform, we've tried to design in a kind of a guarantee of some of these parameters inherently within the system, so you're not trying to control them every time. So for instance, the electrodes are always 6 millimeters apart from each other, whatever the thickness of the electrode. Because you're sitting this on a conventional stir or hot plate, you can maintain the degree of mixing between or within the fluid, and particularly between the electrodes, and also things like the temperature. So those are really important parameters that you want to control for repeatable reactions. So kind of following on from that, really, we went about designing the ElectroReact reactor. As Charlotte said, we called it the bottle reactor initially. And this went through a series of iterations, and we'll be thanking some people later for all of the work they did in that, in breaking and dissolving some of the earlier versions. And what we ended up with this is a really robust ElectroReact reactor. And on the left-hand side, you can see I've exploded an exploded view of these. So if we start at the bottom, there's a glass vial that contains your reaction mixture and a little magnetic flea for the mixing element. There are your two electrodes, and I'll talk about those in a moment. But you can see these are actually, these particular ones in this picture are a mixture of a peak carrier and a foil electrode. And again, I'll mention why in a few moments. The lid insert is really the thing that carries the electrodes and holds the spacing between them. It's actually a really important component in the ElectroReact system. And this gets fastened down onto the glass vial just using a cap. And you can see there's a black O-ring around there, so that's going to provide a gas tight seal. And all of the passages inside, again, are gas tight, so you can maintain this inertness of atmosphere. So I'll just talk a little bit about the lid insert. This has been designed to allow for different thickness electrodes in there. Because the electrodes are referenced on the inner surface, it means that you've always got this fixed gap. So even if your electrode was thicker, you would still have this fixed gap between them. And we can also use this foil carrier, which I'll mention in a few slides. And Charlotte's already talked about this briefly, but on top of the vial lid are the 2 ports that we can use. So you can see 2 electrical connections and 2 ports, and we can configure those in a variety of different ways. So this sort of shows a full kind of schematic almost of what you would need to do an electrosynthesis. So over on the left-hand side is the ElectroReact reactor. So this has been wired up here with a silver wire in there. And I think that's just being used as a reference electrode. And then here we've got a configuration to allow a Schlenk line to be used on there. So this glass vial and the components of the ElectroReact reactor sit within the aluminium plate. So what this ensures is that the mixing in each of the reactors is going to be the same. So there'll be a magnetic flea in the base of each of these, and 1 stir of hot plate will drive mixing within all of these. And we can also maintain temperature, or if we want to, investigate the effect of temperature. Now, one of the features of ElectroReact is it's flexible. So here you could just use a single channel power supply, and you could wire all of these in series to give you the same current through each reactor, or you could wire them all in parallel. So that will give you the same potential across each cell. Or you could do as Charlotte showed earlier and have multiple power packs to control each set of conditions separately. And again, because there's a great deal of flexibility, you can do CV measurements, for instance, using a supplier of a potentiostat. So this just kind of lifts out some of the benefits and some of the features of the system. I'll just run through these quickly. So it allows for parallel reactions, so up to 6. There's really good repeatable stirring and heat transfer. And the bottles are nominally 20 millilitres or 5 millilitres over on the right-hand side. So this is a reduced volume bottle for using smaller quantities of material. It's flexible, so you can use it with any power supply. All of the parts are replaceable. And the fittings actually on the top of this are standard, so you can buy these as standard components from suppliers to make up whatever you want on the top. The electrodes can easily be swapped out for different foils or for plates, and that allows for great flexibility from the user. And I think Charlotte's touched upon this, but we found it very easy and obvious for people to use. We'll talk about some of the support later, but really, coming into a lab, people just, want to be able to pick these pieces of equipment up, use them in a way that their science is going to be very repeatable. And we found that works really well with the whole setup. So I'm just going to talk a little bit about the port fittings on the top. So these are standard 1/4-28 fittings, and you can configure the top in different ways. So you could leave it open. You could leave it open, which would allow you to maybe sample using a needle, or you could fix a septum in the bottom of there, and you would push your needle through the septum. You could blank those ports off, or you could make sampling and addition lines. So here you would take a piece of tubing, that's what's represented by this blue lines, and you would configure 2 1/4-28 inch adapters onto those. So this lower one will get screwed into the bottle, and this other one here has been screwed into a standard Lure adapter for a syringe. And then you can also control the headspace. So particularly if you're wanting to use reactions that are gas sensitive, you might need to purge the reactor and replace what starts off as air, for instance, with an inert gas. And this allows you to do this on a Schlenk line. So again, very convenient and a very nice way, an easy way to really control the environment around which a reaction is taking place. So the electrodes are obviously very important, and Asynt supplying a range of these within their ElectroReact platform. We've had many discussions about a good selection to start with, and they offer, I think, all of these. But the electrodes themselves are a standard size, so 50 millimeters by 10 millimeters, and it'll typically accept electrodes between 1 and 3 millimeters, and actually a little bit wider than that if you really needed to go wider than that. So The reason this has been particularly important to us is purity can be really important of your electrodes. So if we think about stainless steel, for instance, actually when you look at 316 stainless steel, it's actually a mix of metals in that surface. And there's also phosphorus and sulfate in there as well, or sulfur in there as well. So you've actually got to be really careful about the purity of your reaction, that you're not poisoning your reaction, for instance, with some trace constituent that's coming off your metal surface. And over on the right-hand side, I've talked about these foil carriers a little bit already. If you're using things like platinum group metals, which are, actually often used in electrosynthesis, you want high purity materials, but it's obviously very expensive to buy a piece of material like this. Would cost you, quite a few £100s, if not thousands of pounds. So what we've devised is this carrier. So this is made out of PEEK, and it's got these two little notches in it. And we've devised a sort of an origami way almost of folding your foil onto one of these carriers. So once it's done, that becomes a really robust electrode. So you can see in these pictures, this is me doing some early ones actually just with some aluminium foil. And the foil gets locked down onto the carrier, and then you use the carrier in exactly the same way that you would use one of these electrodes. So as I said, that's perfect for your platinum group metals, but it might also be that you have a reaction that there's a buildup of material on the metal surface, and rather than cleaning that off, and the cleaning may be influencing the actual surface of the material that then influences other reactions, you could actually just maybe use a cheap foil. So, things like copper foils, for instance, are readily available and have a high purity. So that could be something that could be of real interest to you. So, Martin said at the start of this that I've worked with Asynt in the past, and we developed the free actor platform. And at the time, we put together a website. And the website was for two reasons. It was there just to show what the equipment is capable of, but it was also there to provide learning and educational resources available to help you get started in these types of fields. And, it's provided, a really useful resource for the free actor platform. I know when I'm working with, people in IPRD and they're coming to Flow for the first time, there are many things in our free actor learning zone that gets them going in Flow and understanding some of the nuances of Flow. And we've tried to do the same thing with the electrochemistry platform as well. So on the left-hand side, you can see is the details about the ElectroReact platform. And over on the right-hand side is the learning zone. And Charlotte will talk about some of those in a moment. But before we go there, I just thought I'd show you some of the support information that's available to you. So this is all of the information that's available to get you up and running with your ElectroReact system. So there are checklists, PDF checklists, overviews of the ElectroReact cell, all of the materials in use in the cell, so you know what the chemical constituents of the vial lid are, or the lid insert, all of those different parts. And then there's a whole series of video clips. And again, these are just 1 or 2 minute video clips. So you can watch these and immediately then have the confidence to go to the ElectroReact platform and start using those. So I'll just show you. So I'm not going to run the videos. You'll have time afterwards to go and investigate that. But there's videos on installing electrodes, configuring the gas environment around your bottle reactor or your ElectroReact platform, how you go about folding and inserting the foil, and that's, again, it's just a 2 or 3 minute job. After you've done it once, it just becomes second nature, and how you go about connecting power. So all really straightforward operations. There's also things that once you've done them once or twice, it becomes entirely obvious, and this just gets you going really quickly. So I think with that, what I'm going to do now is I'm going to hand back to Charlotte, who's going to talk about all of the, or some of the models within the learning zone, and how that can help you make decisions around how long and the kind of voltages and currents you might need within your system.
Thanks, Nick. So as Nick suggested, I'd just like to kind of give a whistle-stop tour around the website. It's pretty vast in terms of the information that's there. As Nick said, both information about the ElectroReact, but information about electrochemistry in general to get you going with what you need. So there are various tabs at the top. So the products that are available.
Sorry, Charlotte, can you share the screen, please?
Sorry, am I not sharing the screen? Sorry, let me try again. Can you see the screen now?
Yep.
Okay, great. So yeah, at the top are various tabs. So you have the products. The operation is the one that Nick mentioned. That has all of the videos in there and the various data sheets. We have a tab on some example reactions, so some papers that we've published using the reactor. There's also this learning zone, which has a lot of information on there about what electrosynthesis is, various controlling factors, but there are also some modelers on there, so you can add, well, let me give you an example. So as an example, the role of the voltage, the current and the time. So when you're doing an electrochemical reaction, the electrons are acting as a reagent. So it's really important to know, or often important to know or understand, how many electrons you're adding to the system. So within this slider, you can, for example, give it the current that you're adding to your reaction. So, you know, you might run your reaction at 50 milliamps. You might run the reaction for, say, an hour. And in doing that, you can get information on the moles of electrons that you've added to your reaction. Similar to that, you can have there's a time estimator. So again, you can add the concentration of your substrate and the volume, so you know how many moles of electrons you need. It might be a 1 electron process, a 2 electron process, etc. The current that you're giving it, and it tells you how long you need to run the reaction for to deliver that number of electrons to the reaction. So you can see if you increase the current of the reaction, you decrease the time that you need to run that for. There are pages on measuring the efficiency. So this might be the conversion efficiency, which takes into account the initial concentration of the reactant and the final concentration of the reactant. Again, how long you've run the reaction for and the current that you've used. And that works out how many electrons you have actually used in converting that reagent, and it gives you a conversion efficiency. And very similar in the yield efficiency, but this takes into account the final concentration of the product. So how many of those electrons, or what percentage of the electrons, have gone into the product. And various other things that you can work out on here. You can even work out the cost of your reaction, so the cost of the electrons that you've added based on the current cost of electricity. Also a really useful one is the wiring. So you might wire your multiple reactions in parallel or in series, and you can add your voltage, your current to this, and it tells you the potential difference in the current in the different reactions, the different reactors, depending on whether you're wiring in series or in parallel. Also really important, scaling your reaction. So this is important in chemistry, it's important in electrochemistry. So as an example, you might do a reaction in 5 ml of solvent. You might run it at a specific current and read what the voltage is. You might run it at a specific voltage and read what the current is. But from that, we can work out the resistance across those electrodes. If you change that reaction volume, you're changing the electrode surface that's in solution, so the depth of the electrode in solution, which of course increases the surface area. And from this, you can work out what new current is required to maintain that same voltage as you used before, or if you're running in constant current mode, what current you need to maintain the original voltage. And then of course that affects the time that you run the reaction for as well. So for example, if this is 2, you have to run your reaction for twice as long as in your previous reaction. So there's all sorts on here. What I do is encourage you to go along and have a look at this. We don't have time today to go through all of it, but have a play around with that. If you're interested in more in kind of the maths behind this, these modelers are very specific to the ElectroReact. So, for example, it takes into account the headspace underneath the electrodes. If you're interested in the maths behind this, then the spreadsheet is there, so you can go away and have a play with that as well. So if we go back to the presentation, I stop sharing. Okay, great. So we just have a short video, and really this is it's a speeded up video, but this is really just to show how simple it is to set up the ElectroReact. So you can see the reagent going into the reactor there, the lid being added, it's connected to a power pack. The solvent has been syringed into the reactor, and then we set the current, and you can see there the formation of an ion complex electrochemically. So really easy to use, very flexible, very reproducible as well. So just before we finish, we really do need to acknowledge people who have worked on this. It's not just myself and Nick who have had these conversations over coffee. There's been people in the lab testing reactors, destroying reactors, telling us what works, telling us what doesn't work. Many students in the IPRD at Leeds, both within our groups and other groups. But in particular, we'd like to thank Hamish Stephen, who's now an electrochemist at AstraZeneca. He did his PhD with us. Christiana, who was a postdoc with us, who now works at BASF. Also the workshop staff in the School of Mechanical Engineering in Leeds. Again, they've made many iterations of these reactors. And then, of course, Asynt for the co-development of what is now the ElectroReact. And then EPSRC, who has supported some of our work through an EPSRC grant. So we'll just leave you with a final slide, which has a photograph of the ElectroReact. There's also a paper there which we published a few years ago, making electrochemistry easily accessible to the synthetic chemist. So again, if you're thinking about, okay, what voltage do I need to start with, or do I need to start with constant current, or what electrodes should I start with? This is a really accessible guide to getting started with electrosynthesis. So I'll leave it there and we'll hand back over to Martin.
Thank you very much, Charlotte and Nick. That's fantastic. Really clear, I think, to help people get started in electrochemistry. And I'm really excited what we've developed together with your guys' knowledge and website, and you know, a really simple but well thought through device. I think it's going to help a lot of people really get started and experimenting in new chemistries they've not done before. So a really big thank you. So hopefully some of you guys listening have some questions, and put them into the chat. I'll pass over to my colleague Catherine, who will see what we've got.
Yep, so we've got a few questions just come in. Firstly, we've got, are there any safety concerns, electrocutions, etc. with this kit?
I can perhaps answer from an electronic perspective. So the power packs would be typically a maximum voltage of 30 volts DC. So that's not high enough to cause significant risk of electrocution. I'm not going to say no risk of electrocution, but it's the sort of power pack we would use all the time in undergraduate teaching labs and those sorts of things without any real concerns or risks. And Charlotte, I guess there's probably a voltage, typical voltages on that you would use in these reactions.
Yeah, I mean, what I would say is the highest risk of doing electrosynthesis is if the electrodes were to touch each other.
Yeah.
And then, of course, you're in a flammable solvent. But the really nice thing is that the electrodes are held very firmly, securely. They're at a fixed distance apart, so there's no risk of them touching each other. So that limits the risk there.
Brilliant. Got another question as well in the chat. Please could we get your thoughts on using the ElectroReact as a teaching tool?
I think it's an absolutely brilliant teaching tool, and it's certainly something that we hope to put into the teaching labs here. Because of its simplicity in terms of being able to use it, so you could teach students very quickly. The nice thing is you get this plate of 6, so you can imagine 6 students setting up different reactors. They're able to compare, different reactions. They're able to compare their reactions across, each other, compare data. I think it's an absolutely brilliant teaching tool.
I think it's probably also worth saying, I mean, the tools that we've designed with Asynt, on one hand, often are quite simple, but there's so much thought that goes into the way that we design them that, they're great research tools and teaching tools as well. I think when we think about teaching tools, we just want something that people can use really easily without breaking them too, they're not too delicate and those sorts of things. So there's a kind of a requirement around making something from a teaching perspective, but they equally match the requirements you need around research in, really reproducible conditions, really controlled fluidic environments, and then the flexibility that comes alongside those as well.
Yeah, it's very good to hear. We don't currently have any more questions in the chat, but if I can just encourage that if anyone has any questions, do feel free to put them in the Q&A or the chat section, and we'll do our best to answer them.
So yeah, I can see the question.
There we
so
go.
I think
Yep.
one question's coming. Can this technology be implemented into flow process? Yeah, absolutely. So I think when I started working with Charlotte initially, we continue to work on flow electrochemistry. So here there are 2 electrodes that are held a fixed distance apart, and a flow path between those. And we have published in that area. So actually, electrochemistry is certainly amenable to flow processes as well.
Brilliant. We've just got another question as well on the vials. Are the vials disposable, and are they standard sizes?
Yeah, I mean, I can probably answer that. I mean, they're made out of glass, so I guess, they're replaceable. I probably wouldn't say disposable. And there are 2 sizes that I think are on offer. So there's the standard, so we've called them the 20 ml and the 5 milliliter vials, but nominal values those. So the larger and the smaller ones, they both fit the same cap and the same lid insert. The electrodes would fit in both of those, so you can switch between those quite easily. And I think what Charlotte's also demonstrated in the website was we've come up with a model that should help you move up in scale or down in scale if you really wanted to between one size and the other. I mean, it is quite specific to the ElectroReact because some of the assumptions you have to make are about the degree of mixing, but between our 2 sizes, I think they're fairly good assumptions. So yeah.
And just going back to the disposable nature, they're glass, so you would clean them like you would clean any of your lab glassware. So we certainly soak them in the acid bath like we would do chemical reactors, and give them a good rinse afterwards, and then we can do our synthesis, we can do our CV in them.
With the Electrosyn, we've seen contamination of the reaction mixture with metal coming from the attachment points from the electrodes. Can this be prevented with this setup?
I mean, I can answer from a sort of mechanical perspective, Charlotte, but you've more from you. I can start with that. So yeah, I mean, I can't really comment on the Electrosyn, but the way our electrodes sit within the system is there's a stainless steel connecting pin, if you like, that goes through the cap, and that has gas seals around it so that it's really robust. And the electrode face just at the top of the electrode bolts up to that. So obviously that's in the cap element of it. Actually, I can probably show you, over on the picture. So that's in the cap element of it. So yeah, I mean, technically there is stainless steel, for instance, in all of the reaction environments, but it's right up at the top. So if your liquid level is down here, then I guess unless you've got kind of vapor maybe condensing at the top, then I think you're probably okay. But I don't know, maybe you found different things, and maybe your environment's a bit more challenging. So whether it would be possible or not to plate those, I don't know, but that's maybe a discussion for a different day.
Yeah, certainly for all the chemistry we've done, you would have to have your solution right up at the cap for that to happen. We've never seen contamination, and we have done reactions with stainless steel electrodes, so we know what that would look like, and we've never seen contamination from that stainless steel.
Very good.
So we've actually got a follow-up on that. Are there currently options for softer foam materials available? They can imagine that the locking mechanism might squish those materials.
Yeah, so I'm guessing here you might be thinking of something like a metallic foil or a nickel kind of foam, for instance. So we have used nickel foams within these leads. I think if you were using a particularly soft material, what you might need to do is place a small backing plate. So instead of the grub screw driving directly onto the material itself, it drives onto a little plate, and that would spread the load to some extent. And I think you would be able, it depends how soft it is and what your foam material is and how brittle it is, but I think that would probably allow you to do something like that.
Another question is,
oh, sorry, I was just going to say I spotted another one there as well, but you go for it, Catherine. So.
Thank you. Can immobilized catalysts be used too, or does the catalyst need to be in a homogeneous system?
If you have your catalyst immobilized on a material that fits within those ports, then yes, an immobilized catalyst can be used. But I guess that's something, whether you normally make your catalyst, your support would need to fit within that slot that the electrode goes into.
Thank you, Charlotte. I think we've got a question coming on the chat regarding cyclovoltammetry. The software has to come from the potentiostat being used. Is that correct?
Yes. Yeah. So different potentiostats will come with different software. So yes.
I think that might be it then for questions.
Thanks again, Charlotte, Nick. That was fantastic. Really appreciated, and I think really clear to help all those in the chat to understand what's been put together here and how it can work, and get people started in the electrochemistry area, which is great. And so thank you to everyone who's joined us today. Really hope that you found this of interest. A recording available, so please drop an email to inquiries@asynt.com if you want to have a copy of that. And of course, if you want pricing or a bit more information on the packages available to purchase from Asynt, and also drop an email to inquiries@asynt.com and we'll see how we can help you. But again, once again, thanks everyone, and hopefully we'll see you on another webinar when we've got some more new products.